Welcome to Engineering Mechanics video lecture. In this video lecture, I am trying to explain you about answer for kinetics of curvilinear motion problem. I read the problem one time. Find the value of the angle pi defining the positions of the point B where the particle will jump clear of the cylinder surface after the string OA has been cut. Neglect friction. On observing this problem figure, we can understand that one semicircular cylinder surface is there which is placed on the horizontal ground, and the weight of W particle which is suspended by means of a string OA of radius L. OA is making a alpha angle with a vertical line coming from O. The radius of cylinder surface consider as R from here to here. The particle of weight W contacting cylindrical surface at point of contact A. When you join a line from point of contact A to center of this cylindrical surface, consider as alpha. When you join a line in between point of contact in between weight of particle W and center of cylindrical surface is considered as radius of cylindrical surface. This radial line is making a alpha incline with vertical line. After the string OA has been cut, the particle A of weight W may move in this direction from A to B in curvilinear path. While it is moving from A to B in curvilinear motion, at the contact, normal reaction force will be generated. By following the direction of motion from A to B, tangential acceleration taking place and also normal acceleration taking place. The direction of normal acceleration is directing towards the center of cylindrical surface. Normal acceleration of the particle is directing from here to in this direction. Tangential acceleration directing from here to in this direction. Along the tangential acceleration direction, velocity of the moving particle also directing from here to in this direction. Opposite to normal acceleration, from here to in this direction, centrifugal force will be generated. Opposite to tangential inertia force will be generated in this direction. At the contact in between a particle and a cylindrical surface, normal reaction force will be generated. According to this problem, up to reach B position, the radial line drawn from B point to center of the cylindrical surface is making pi incline with vertical line. In this problem, we have to find the magnitude of pi. To find that pi value, we have to apply the equilibrium equations along normal acceleration direction and also energy conservation equation. While the particle is moving from A to B in curvilinear path, we have to estimate potential energy and kinetic energy of the moving particle at A position and also at B position. After the string OA has been cut, the particle which is start moving from A to B and then after jump clear of the cylindrical surface. At the time of leaving cylindrical surface, the reaction force generated at the point of contact in between particle and cylindrical surface considered as 0. When you draw the free body diagram of particle of weight W at particular point B, final position of the particle at the time of leaving a cylindrical surface, we have to get exactly like in this fashion. At the contact in between a particle and cylindrical surface, for the final position at B, the reaction force generated is R considered as 0. When you join line in between position B to center of cylindrical surface, this line makes pi angle with vertical line. We have to consider the weight of this particle is directing downward direction. The angle made by the weight force with this radial line is also considered as pi. As this weight force is making pi inclination with this radial line, we can estimate a component of force along normal acceleration direction an is considered as w into cos pi. Along perpendicular to normal acceleration direction, along tangential direction, we have to get a tangential component of weight w into sin pi. Along the tangential direction, for the particle velocity taking place in this direction, and also acceleration tangential taking place. Opposite to tangential acceleration and tangential velocity, inertia force will be generated in this direction, mat. While the particle is moving from A to B in curvilinear motion, at point B, normal acceleration taking place towards the center of cylindrical surface. Opposite to normal acceleration direction, inertia force will be generated in this direction. That is also considered as centrifugal force. It is estimated by following the mass of the particle into normal acceleration man. By following weight of moving particle W, we can estimate mass. Weight equal to mg. From that equation, mass equal to W by g. In this problem, we are going to find the angle made by the radial line drawn from final position B to center of the cylindrical surface with vertical line phi, by applying equilibrium equations along normal direction and also conservation of energy. When you apply summation of the forces along normal direction, we have to consider the force which is directing along normal acceleration direction considered as positive. The force which is acting opposite to the acceleration, normal acceleration, considered as negative. So that we can get final equation along normal direction where r is 0 and m is w by g. Normal acceleration an of the moving particle in curvilinear motion is the function of tangential velocity v. We can estimate that normal acceleration by following v square by r. When you substitute in this equation an as v square by r, we can get w into cos pi equal to w by g into v square by r. In the right side of the equation, w is there. In the left side of the equation also w is there. Cancel w. Finally, we can get cos pi equal to v square by rg. By following dynamic equilibrium along normal acceleration, we have founded cos pi as v square by rg. Using derivation of energy at position A and B, we have to get another equation of motion in terms of V, so that we can estimate uh, potential energy at position A and kinetic energy at same A. When the string OA has been cut, the particle of weight W connected with this string start moving from A to B and jumps off. In the travel from A to B, it moves in curvilinear path. While it is moving from A to B, energy change taking place. At position A, the particle total energy estimated by following potential energy and kinetic energy at position A. Potential energy at A follows vertical height covered by the moving particle with respect to horizontal ground. When the particle starts moving from A to B, energy change taking place. At A, the energy possessed by the particle is considered as E1. Up to reach B, the energy possessed by the particle is considered as E2. E1 includes potential energy 1 and kinetic energy 1. E2 includes potential energy 2 and kinetic energy 2. Potential energy of the particle at position A can be estimated by following the height about the ground. The about the ground up to position A considered as HA. By following this triangle, right angle triangle, we can estimate this HA by following this. This side is considered as HA. By following this radius and angle, this is the adjacent side. We can estimate by following cos alpha. Cos alpha into this radius R giving us HA. PE1 equal to mgHA. mg indicates as weight of the particle. At position 1, the kinetic energy Ke1 is 0. Therefore, total energy at A position E1 equal to W into HA. Then after we can estimate potential energy at position 2 at B. It is also follows vertical height about the ground up to B. It indicated as HB. HB exactly equal to R cos pi. Using this right angle triangle, this radius is making pi angle with this vertical line. We can estimate this HB by following this triangle. The radial line from B to center of cylindrical surface is R. The angle of inclination with vertical line is pi. This is adjacent side. We can estimate this adjacent by following cos trigonometric ratio cos pi R into cos pi giving us HB. By using this HB, we have to estimate potential energy 2. It is exactly equal to mgHB, where mg indicates as weight of the particle. At position B, the kinetic energy possessed by the moving particle of weight W is half mv square, where m indicates as mass of the moving particle. In terms of weight of particle W, we can write it as W by G. Therefore, total energy at B E2 equal to W into HB plus half into W by G V square. By following conservation of energy, we can equate total energy possessed by the moving particle at position A exactly equal to total energy possessed by the moving particle at B. E1 equal to E2. On substituting these two values, we can get WHA equal to WHB plus of W by G V square. In the left part of the equation we have W, in the right part of the equation we have W, cancelled each other. HA equal to HB plus V square by 2G we can get. Take HB to the left side of the equation, it turns minus. We can get HA minus HB equal to V square by 2G. On substituting HA value and HP value from the free body diagram, we can get final equation R cos alpha minus R cos pi equal to V square by 2G. By using dynamic equilibrium, we have estimated cos pi as V square by Rg. By using this equation V square, we can find it as Rg into cos pi. When you substitute this V square equation in terms of R and G cos pi, R cos alpha minus R cos pi equal to Rg cos pi divided by 2G. G cancelled. In the left side of the equation we have R common term. In the right part also we have R. R also cancelled. Finally we can get cos alpha minus cos pi equal to cos pi by 2. In the right part of the equation 2 is dividing cos pi. When you take that to the left side of the equation, 2 multiplies cos alpha minus cos pi. In the right part we have to get only cos pi. When you multiply with 2, we have to get 2 cos alpha minus 2 cos pi equal to cos pi. Finally, 2 cos pi plus cos pi equal to 2 cos alpha we can get. In the left part of the equation, 2 cos pi plus cos pi giving us 3 cos pi. 3 cos pi equal to 2 cos alpha. From that equation we can estimate cos pi value. Cos pi value exactly equal to 2 by third of cos alpha.